Today we are going to be learning about a principle of equilibrium called Le Châtelier's principle. It's a French name. I think I spelled that right, but I think there's an E in here. My bad. Okay, Le Châtelier's principle. Le Châtelier's principle, it's important to not necessarily know the name or be able to remember it or how to pronounce it, but you have to know the chemistry behind it. So what does this principle tell us? It's going to instruct us how our reaction is going to return to equilibrium. So, all systems strive for states of equilibrium. That means that a chemical reaction will keep going until it reaches the point where it won't react anymore. That's what equilibrium is. And so we learned last time that some reactions, equilibrium is after all of the reactants have been used up. Some reactions, equilibrium happens before that, though. But if a system is at equilibrium, it will try to regain equilibrium if that is disturbed, and that's what Le Châtelier's principle is. So let me write that down, and then I'll explain it again. If a system in equilibrium is disturbed, the chemical reaction will shift in some direction to regain equilibrium. If a system in equilibrium is disturbed, the chemical reaction itself will try to fix the disturbance that was caused to take it out of equilibrium. So the point of this is that all of our systems are trying to get into equilibrium. They want to be in that place where everything is, like for them, for the chemical reactions, like neat and tidy. Okay, so if you have a writing utensil, you're going to need that. For our little demo, I'm going to use a meter stick. Okay, so this is how Le Châtelier's principle works. In any chemical reaction, we have reactants on the left and products on the right. A chemical reaction that is in equilibrium is like a teeter-totter. Do you guys know what a teeter-totter or seesaw is? Have you ever played on one? I know, like, they've taken them out of playgrounds because, like, the adults are afraid that you're going to hurt yourselves. Has anybody not ever been on a teeter-totter? It's a seesaw. Yep. Okay, good. Okay, so everybody has, yes, Mason?
I just looks like there was one time where one kid sat beneath the one side of the teeter-totter.
Oh, yeah. If you play stupid games, win stupid prizes, I feel like that's natural selection right there. Okay, so if, my friend, you and your friend are on either end of the teeter-totter, what happens if you jump off? If you're on this end and you jump off, what'll happen? Mason?
They'll go.
They're going to hit their butt really hard on the ground, right? It's the same thing in a chemical reaction. So let's talk about the 3 different things that we can do to disturb equilibrium. 3 equilibrium disturbances. I'm going to move you 2. you're testing my patience to the utmost. Thank you. The first thing that we can do is we can add or remove products or reactants. Oops. Okay, so if you use your pencil and pretend that it's a teeter-totter to help you think about your chemical equation, this will help you answer these problems. So whenever you're adding a chemical, it'll be like adding a kid to the teeter-totter. So the first thing that we could think of is, what if we add a reactant? Well, that would be like adding a kid to this side of the teeter-totter. If we add a kid here, what'll happen?
Down that side.
This side goes down, and this side now is up in the air. What would we have to do to get the teeter-totter back to equal? Mason?
Add products.
Add a kid on this side. So whatever direction, like if you're using your pencil and you're thinking about where did I add a kid on which side of my pencil, of my teeter-totter, whichever side is pointed in the air, that's the way your reaction will shift. So you're right, when you add a reactant, you're going to shift to the product side. In other words, your reaction is going to say, oh, there's more reactants. We need to now make products to balance out the teeter-totter. Does that make sense?
Yeah.
Okay, so then what happens if you remove a reactant? Well, that would be like taking a kid off of this side of the teeter-totter. If you remove the reactant, this side will go up. And so which way will your reaction shift now? To the left or to the right? To the left. Now, the opposite is true when you're thinking about products. But we can write those down as well. If we add a product, that's like adding a kid to this side, so that means this one will go down. Your reaction arrow always goes now to the point, to the side of your teeter-totter that's up in the air. So you're going to shift to the left. And then if you remove a product, you're going to need to remake that product. And so your reaction arrow will shift to the right. When you get to homework questions, these blue arrows are all you need to answer the question. So if you just show an arrow to one direction or the other, that's all I'm looking for. So that this would be like page 4. We'll do examples, but not until after I've taught you the 3 disturbances, okay? Now, there is one thing. What if you add equal amounts, or I guess if you remove equal amounts, of a reactant and a product? What will happen to your teeter-totter? Nothing will happen. So that would be like, this would be a fun physics experiment. If you and your friend were on, and you weighed the same, you were on a teeter-totter and you tried to jump off at the same time exactly to see if you could get the teeter-totter to like not move at all. So nothing will happen here. So what you should write is like no change, or you can write a big equal sign too, that's okay. Whatever you want to do, just make sure that it's legible so that I can read it. If you've got 2 random lines, like maybe, I think I prefer maybe no change. Actually, thinking about some of your penmanship, maybe we should just write no change. Okay, so this is the first kind of disturbance. That's the easiest one. The second kind of disturbance is like medium hard, but it's not if you think about chemistry. So changing the temperature of a reaction can be a way to shift equilibrium as well, but only if your reaction has heat involved in it somehow. So let me explain this. Let's start with for exothermic Do we know what the word exothermic means? Heat is leaving the system. For exothermic reactions. So what does that mean? If heat is leaving the system, and here's my chemical equation, is heat a product or a reactant? Right?
Product.
It's a product. Well done. Okay, so now that we know this, if you think about heat as a product, as one of the kids on either end of the teeter-totter, your answers are going to be the same as if heat was just any other product. So for an exothermic reaction, if you increase temperature, what does that mean? You're going to add another product. So in an exothermic system, if you try to heat it up, it'll actually go in the opposite direction. Because that reaction wants to make heat, and if you're giving it heat, it has no reason to do any more work. It would be like if your job was to make money, but somebody just gave you money, why would you make the money? You were already getting it. Mason?
So does that mean there are certain like exothermic reactions that you can really halt by having them in certain temperatures?
Mm-hmm.
That's good. I knew that.
So if you decrease temperature in an exothermic reaction, it would be like taking that heat product away. And so if that's the case, your teeter-totter then says that this is the side that's pointed up. Your reaction must shift to the product side. So if you have an exothermic reaction, you've got to cool it down usually. When I make acids for our labs, that's such an exothermic reaction that I have to usually make an ice bath. Depends on what kind of solution I'm making. But if I'm using like the stock HCl, it's such an exothermic reaction that if you don't cool it, it'll actually break the glass. So some things you just have to cool down in order for them to progress. Now, all of this is true, but in the opposite for endothermic reactions. Endothermic reactions then require heat in order to progress. And so that would make heat a reactant. Because you need it. Your reaction can't progress without it. So now here, if you were to add heat or increase your temperature, that would be like adding a reactant, which means that your reaction will shift to the right. And lowering your temperature means that you're taking away a reactant, and that means that the reaction can't progress. Any questions about the temperature disturbances? So just think about heat as a product or a reactant, and it's the exact same as it was for adding products and reactants. The third disturbance, though, is not anything like it and can be pretty tricky. You're going to have to memorize a little something for me. But that's okay because I make you memorize so little of things. And it's good for you. All right, so pressure changes. This can be really tricky. If you're taking AP chemistry next year, or if you want to take chemistry in college, you got to lock in on this because this is like a critical concept that they expect you to know always and till the end of time. So brace yourselves. Okay, so when you're looking at a pressure change, let's firstly do this. If pressure increases, what happens to volume? Volume decreases. So just remember these two things, these two relationships, because sometimes I will give you a problem where I say the volume of the container is increased. If the volume of the container is increased, I'm, in other words, saying to you, I've decreased the pressure. Okay, so I'm going to write the rules down, and then we'll talk about them. If pressure is increased, what does that mean? It means that you have somehow compressed the reaction to cause that pressure to increase. And if that happens, in order to try to regain equilibrium, the reaction is going to shift to the side of fewer gas molecules. So the reaction will shift. So your reaction arrow to the side, oh my gosh, to the side with fewer gas molecules. So the reaction is going to try to alleviate that pressure, and it's going to try to do that by just making fewer gas. Yes, Mason?
And is that rule like infallible among all reactions? Or is that, okay.
It is. The only thing that I would say that would be an exception to that is not every reaction has gas molecules. But if you don't have a gas in your system, can you really compress it? No. So that's kind of a red herring anyway. Okay, so when you get a problem like this, you have to look at how many gas molecules there are in a reaction. So let me give you a reaction here quick. I guess we have to balance it. Nope. Oh, yes, we do. I don't know what's wrong with you. Okay, so I'm going to increase my pressure. Which side should my reaction shift to? Well, let's look at how many molecules of gas do we have. How many H2s do we have? 2. And how many O2s do we have? So how many total do we have? So all you have to do is add the stoichiometric coefficients of the gas ones. But don't add them for liquids and solids, only for gas. So how many gases over here? Okay, so my rule says shift to the side with fewer gas. Which side is fewer? The right side. So that's which way it'll go. So just add your numbers and check which one's smaller. That's the way it goes. Now, it's opposite for if you decrease the pressure. If pressure is decreased, you're going to shift to the side with more gas molecules. And remember, this can be only gas molecules are considered. If you don't have any gas molecules at all in your reaction, nothing will happen. But, yes, sir.
So, is a shift like adding gas or like reducing gas?
So, good question. What'll happen here if the pressure is increased is that these reactants, if there are any left in the container, are going to be more incentivized to react together to form this.
Okay.
So it would be like, imagine, Ray, that you are in a room and there are only 3 people in the room and none of them are like your best friends. But then I came into the room and said, like, I increased the pressure of the room and I said, if you don't pick a friend right now, I'm going to charge you $50 to leave the room. You're going to pick a friend because at that point you're just going to be like, all right, well, who cares? I don't want to pay $50. So that's the same kind of thing that's like going through, not, they don't have minds, but like that's what it's like for these molecules. They maybe didn't want to react before, but now you've incentivized them to do the reacting. Okay, let's do some problems from your homework now so that you have a good start. Page 4. Let's just start with number 10.
Should have paid attention.
Let me... Is this reaction balanced? Okay, good. I thought that they all were, but then I got the fear. All right, so let's go through each one of these parts of the problem individually. Part A wants to know if the pressure of the system is increased, what will happen? So we just want to know if there is a right arrow, a left arrow, or a no change. Okay, so if we're increasing pressure, that means that, looking at my rules, I'm going to shift to the side with fewer gas. So I need to go back to my reaction and count how many gas are on both sides. How many gas on the left? How many gas total on the right? All right, so which side is fewer? That's the answer.
That's it.
That's it. All right, the volume of the container now is increased. What does that mean that what will happen to pressure? Decrease pressure. Okay, so now we're going to shift to the side with more gas. Which one has more, left or right?
Right.
That's your answer. Okay, so now for C, D, and E, we have like teeter-totter problems. So now we just need to figure out where on the teeter-totter these things are. So N2O3 is a reactant, so that means I'm going to put a kid here. So which way should your arrow point? To the right. Oh. Dang it, why did I do that? To the this way. Okay, let's do the next one. D is NO, but it is removed. NO is a product, so we're going to take somebody off of this side. Which way should our arrow point? To the right. And then E says NO2 is added. So NO2 is a product, kid on this side. Which way should our arrow go? To the left. That's it. Yes, sir.
So when you're saying what, no gas, is that like no gas at all? Because I'm looking at 12 and it has one side has no gas, the other side has 2. So
Yeah, let's just let me break that one on the board. That's a good example. So Mason asked about this reaction here. Okay, so Mason, how many gas do you have on this side? 0. And how many gas do you have on this side? So then that's how you'll compare. So if you increase pressure, you'd shift to the side with fewer, and 2 is less than 0.
And if there's any special rule with it being no gas on this side?
Right, yes, nope, that is how it is. Now, my friends, I have one more thing for you. And this is really important. So I need you to listen carefully. Because solids and liquids do not appear in KEQ, adding them will not affect the teeter-totter. Let me say that again. Because solids and liquids do not appear in KEQ.
This KEQ.
What?
What's KEQ?
That's what we learned on last time. These do not disturb equilibrium.
Is there any solids and liquids in here?
There are. There's one, I think, on number 12. So if it says on number 12C, NH4HS solid is removed. It's a solid, no net change.
Oh,
The reason is because solids and liquids do not appear in the equilibrium constant. So adjusting them can't affect equilibrium.
wait, I have a question.
Yes,
Remember E?
on which one?
12, on 12?
Uh-huh, yep.
Since there's equal amounts, wouldn't it still run that way though?
Yes, but one of them is a solid.
Yeah, that's what I'm asking.
Yep, so it's like really, you're adding equal amounts, but it would be like, this one doesn't do anything
That's
now.
what I'm asking.
So just, it would be like adding on this side, so it would shift to the,
Okay.
yes, Ray.
So the zero just like, so 2 is less than the 0 for some reason?
No, there are 2 gas here and then 0 gas. 0 is less than 2. So if you are increasing your pressure, like in part B, the volume is decreased, which means pressure is increased, you'll shift this direction
Okay.
because you have to produce fewer gas, and 0 is fewer than 2.
It's the other way.
What other questions on page 4 do you have for me?
So wait, so for 12, what are the answers?
I didn't do them. You can do them. Yes, Hunter?
I don't know if I'm thinking about it wrong, but why is there no gas on the left side?
Because on the left is a solid.
Oh, there's ledger. Never mind.
Yeah, it's dark in here. You might have to get close.
Alright.
Wait, I have a question.
Yes, Kaden.
On 13 and 11, it's where one of the things is taken away, but then it's equal. Like both of them have the same amount.
Give me an actual.
So on like 11, it's 2 NOBR. The reactant product is 2 NO and then BR plus BR.
Yeah.
And then for B on that one, it says NO is added.
Mhm.
So wait.
So if NO is added, NO is a product. So you'll add
Oh,
something. So it'll shift to the left.
Yeah. No. Wait. Which one was I confused on? Oh, here. No, on number 13.
Okay.
So it's NH3 plus HI and then the arrow NH4I. So
Yep.
then it's 2 on the left, 1 on the right. But then it says HI is removed, so then they're equal. So then.
Right now this
Okay. But
Oh, how?
it's equal with at the start we're like it's equilibrium ratio. Think of it like
I'm gonna stop the video and I'm gonna help Kaden.